A note about the exams. With a bin width of 10, that is fairly skewed.
To the left, I can see how all the weights for it.
All the way up at the top, so that's a skew left distribution. But that's a pretty nice average in my opinion. It's a moderate standard deviation, but I'm gonna say pretty good. The only thing that disturbed me was that only 9 people actually read all of the instructions. So if you've got questions regarding the exam, please don't hesitate. You come ask me about them. And I will happily discuss the exam. I did post the key to our Canvas page. So if you're going, well, what was he looking for? And what the hell were with those bonus questions? I promise it's all there. I did try and pick movies that were recent enough in your life that they should have been things you might recognize, but they were a long shot. I didn't pick that. Sure. Good. Thank you. Okay. I want to talk about probability distributions. We were talking about this at the end of class on Wednesday. Let's think about the way in which we create a larger view. Rather than just looking at the probability of an individual event. Let's consider our experiment, right? Whether it was flip a coin, roll a die, pick a card. I'm going to define a random variable. A random variable represents the outcome. From my experiment, my random process. You'll often hear this referred to as a stochastic process. For now, we're going to deal with discrete random variable. All right, wait a minute. Data type, discrete. What's it mean to be a discrete data type?
It has a countable number of distinct values. Like you see it from the number of emitted exterior to absolute row. Like you said, x is 0, 1, 2 up to 80.
Perfect. So a discrete random variable, countable number of outcomes. It may not have a clear upper limit. I could ask about number of phone calls. You can't make half a phone call. But if nobody answers the phone and you dial each number, let it ring once and hang up, you could make 1,000 phone calls in a day. It's probably not reasonable, but you could. So my goal is a discrete probability distribution. We often refer to these as probability distribution functions, in which case I'll abbreviate it as a PDF. Has nothing to do with opening a file of any type. So if I have a discrete random variable, X, my probability distribution assigns each and every one of those values of X some probability. Maybe a little more formal. If my sample space has the values x1 through xn, then I will have the chance that x equals one of those values. Because these are simple outcomes in my sample space. I'm picking a card. There are 52 possible things it could be, right? I'm rolling a die. There are 6 possible things it could be. What I have to know each of those is a valid probability. That means they're a value between 0 and 1. And if I add them all up, I should get 1. So I could say, I've got a rigged coin. My probability distribution looks like this. This coin is rigged to land heads 80% of the time and tails 20% of the time. Each number is between 0 and 1, and when I add them together, I get exactly 1. This is a valid probability distribution function. It assigns a value to each of the options in my sample space. So let's think about what could happen if I flip a coin 3 times. And my random variable, what I want to count, is the number of heads that could occur. So, hold that thought. What I need to do before I build the probability distribution is I need to know what sample space is. What are the possible things that could happen? You have a fair coin. You're going to flip it 3 times. You're going to count the number of heads. What are my options for X?
I get either 0, 1, or 2, or 3 heads.
Perfect. My sample space, 0, 1, 2, 3. But those are not all simple events. I'm not even, you know what, let's not even call this a sample space. These are the X's I could use. This is the set of possible outcomes for X. Because really, that isn't my sample space. I flipped the coin the first time. That's chance, right? Flip the coin the second time. Flip the coin the third time. Does what happens in the third flip of the coin care about what happened in the second flip of the coin? So they're independent of one another. And if they're independent, I can count how many options there are. My probability rules, right? The stuff we did on Wednesday. I can do my counting options. How many options are there out of the first flip?
3 options.
If I'm just flipping a coin, there are only 2 options. Right. And then there's only 2 for the second flip, only 2 for the third flip. And since I want this and this and this, a total of 8 possible outcomes that could happen. Now, if I really want to go through and count them all differently, so I know what's going on, I need some way to write out this idea explicitly. I'm going to use a tree. We could use a number of different options, but I'm going to use a branching tree. So let's think. I flip the coin the first time. It either comes up heads or tails, right? There's flip number 1. I flipped the coin the second time, but I've already flipped it the first time. So I'm either going to get a heads or a tails here. But I also have that same option with the first coin being tails, because the second coin doesn't care what the first coin did. And then I keep going. Flip 3. Now, starting all the way over here on the left, read down the branches all the way to the right until you get to the ends, the leaves of our tree. Stretch this metaphor as far as I can take it. That top set of branches, 1 option. This set of branches leads me to 3 heads, doesn't it? The next set of branches leads me to 2 of them. So does the next set of branches under that. Remember, I'm just counting the number of heads, right? Keep counting all the way across. So now you can tell me, for each of the options 0, 1, 2, 3, for x, my random variable x, which counts the number of heads, as those options, what are the corresponding probabilities? What's the chance I get no heads?
An eighth of a chance to 1/8 or 12.
1 out of 8. 1 heads happens 3 times out of my 8 options. 2 heads happens 3 times out of my 8 options. And 3 heads happens 1 time out of my 8 options. Again, assuming a fair coin, assuming independence, that I'm not throwing the coin in some rigged fashion. This is my probability distribution. Again, assuming a fair coin. Questions? But now that I have this, you can answer questions about this. You're going to flip a coin 3 times. What's the chance you get 1 head or 2 heads? 6 over 8. Because 1 or 2, they're disjoint options, there's no overlap, right? So they're separate and I just have to add them. There's my rule for or, right? For unions, the probability of A union B is the probability of A plus the probability of B minus the probability of both. But there's no way to have 1 and 2 at the same time as your result.
Is it -0? Just because we can't, like, that's not.
I asked you to have 1 head and 2 heads out of 3 flips. I can't do that, can I? In a case like this, where these are all mutually exclusive outcomes, there's no way to have 1 and 2, or 1 and 3, or 0 and 1. None of these can overlap at all, right? So if I ask, what's the chance of getting less than or equal to 1 head, all I need to know is all the outcomes that go into that, right? Okay, I apologize up here. This was a little sloppy of me. I should have written X equals next to all of those, right? Because I'm thinking of the value. I really should say it, the chance that this variable is equal to that value. But I know those numbers right off of my distribution. Yes? That's easy. 1 out of 8 plus 3 out of 8 is 4 out of 8, or 1/2. Even if I don't know what the distribution is going to represent, I claim this is a probability distribution. But before we do anything else, you should determine whether or not I'm lying. How do I know whether or not this is a valid probability distribution? Well,
We have to be after 1 probably, it can't be like a probability of 1.2.
it can't even be short, right? It can't be 0.95. I've got to have everything. And each individual number has to be between 0 and 1. Well, I'm sure all of the individual numbers are between 0 and 1. Add them up. They don't add up to 1, up somewhere. 30 and 30 is 60, 70, 80, 95, 100. 1.00. It worked. Probability distribution function. That's what I'm going to use PDF for that all the time. But now I can start answering questions the same way we did before. Now, some of these are a little easier than others. And some of them are actually the same. Probability of X bigger than or equal to 3.
Yeah, 40% chance.
Because it's
0.2 plus 0.15 plus 0.05.
chance of 3 or 4 or 5. Great. The next one, I can actually answer in 2 different ways. I could do the same thing we just did, right? I could take 0 and 1 and 2 as options. But notice that 0, 1, and 2 is everything except 3 and 4 and 5. What do I know about every probability distribution? If you add them all up, you get 1. These two events are complementary sets. It's everything bigger than or equal to 3 versus everything less than or equal to 2. That splits the whole thing exactly in half, doesn't it? Not in terms of probability, but in terms of the outcomes. So what I could say is I could say this is the same as 1 minus chance that's bigger than or equal to 3. Oh, that's sneaky. That's sneaky. 1 minus 0.40 is 0.60. But if I did it the other way, 0.05 plus 0.30 plus 0.25 is also 0.60. That's the same result. How do you want to get at it is up to you. Now, I did say that this gives me the different ways to write things. I just realized that I actually wrote this one incorrectly because what I wanted to write here is not less than 4, but bigger than 4. Is that right? Oh, crap. I think I screwed it up again. Let's do it this way. If I want bigger than 4, well, then I leave off the equals part, right? So this is 5 and 6, and I've got that. I'm sorry, it's 5 only. Probability of X equals 5.05. If I had strictly less than 4, would be 1, 2, and 3, wouldn't it? 0, 1, 2, and 3. That was the opposite of that. What about that bottom one? Well, that's a single dot, right? I can just read that right off, 0.25. The less than or equal expressions come up so often that we can think of this in a slightly different way. Let's go back to our descriptive statistics. We talked about frequency distributions when we did histograms, right? We had those charts with the bins and all. We had a frequency distribution. And if those were in order from smallest to largest, when we did the histogram, we had that curve, right? That OG, the red line that showed up on my histograms. And that accumulated stuff. Now, here's again where it really benefits me to use numerical values as opposed to qualitative values. Like if I had, I don't know, what color is someone's car, this wouldn't be a good idea for that. You know, it's like, what do you mean yellow is bigger than red? Doesn't make any sense. But let's go back and look at the probability distribution we were just looking at. I'm going to change the second line. So we're going to take this table, which was the probability distribution function, and use it to build a new table. What is the chance that x is less than or equal to 0 based on that table?
You 0% chance.
Oh, hang on. Less than or equal to 0
5%.
means it could be equal to 0, so 0.05. And when I get here, there's a 30% it's equal to 1, but there's a 0.35 that it's less than or equal to 1. And then when I get here, 35 add the 25, I get 0.60. When I get here, do you see how I'm building by adding on the next one in the line? By the time I get to the end of it, I've got a 1. This is doing exactly what that curve ogive thing did in our histogram. This is called a cumulative distribution function, and it corresponds to the PDF we were just doing, so we're going to call this a CDF, cumulative distribution function. Yes, sir.
You would only use this when it's x is equal to or greater than or less than.
Less than, right. But I can do it for other things, right? If I wanted to know what is the chance of x being bigger than 4, right? That's the same as 1 minus the chance of the complement, isn't it? So I can use it for strictly bigger than or strictly less than. I can do a lot of other things here. So there are utilities where sometimes it's better to have the CDF, sometimes it's better to have the PDF. I like PDFs more, but I'll use CDFs rather frequently for exactly this sort of cut it off behavior. If I wanted the probability that x was equal to 3 and all I had was the CDF, how could I get that? How can I get back the chance of just being 3 when this is the only piece of information? Chris?
Would be all of them like 0, 1, 2, 4, 5 minus 3. Like so like I guess just 1 minus 0.8.
Well, that would give me everything up here, wouldn't it? That would give me the things that were bigger than 3.
Is it just what's in 3 minus 1?
Well, that's going to give me something negative. And probabilities have to be between 0 and 1. But I like the subtracting idea. If I just want 3, I could start with the chance that it was less than or equal to 3, right? That would give me all of that. But what don't I want? Leo?
You don't want it to be other numbers than that x is 3. You only want it to be only that number only.
So I need to take away
The other numbers around it.
those. So you see, Chris, I can use a CDF to build a PDF. I use a PDF to build a CDF. They're actually interchangeable in a lot of fashions. 0.80 minus 0.60 equals 0.20. Now, we will, over the next couple of days, look at several PDFs and CDFs that I use a lot. But when I think about probabilities, I spend a lot of time thinking about averages and variation, standard deviation, things like that. So I would like to be able to say, if I have a PDF or a CDF, which will give me a PDF, how can I get things like an average? What behaves like an average here? Well, there's this idea called expected value. And this really does give me a measure of center for a PDF. I've used the word mean here in quotes. With a little bit of calculus, I can take those quotes away. It turns out that this idea of expected value is exactly the same as averages. But it's an average for probabilities. So the way to do this is to take into account the value as well as the chance of it happening. So the way to get this average, this expected value, is to take each value itself, multiply it by the chance of that happening, and then add them all up. So this is not just an average, it's a weighted average, right? It puts more weight towards larger numbers and smaller weight towards smaller numbers, so that I'll get a value. This might not actually be a value that is possible. It might be between things. I'll give you a nice straightforward PDF. We're going to roll a die. This is a normal fair die. So the chance of X coming up 1 or 2 or 3 or 4 or 5 or 6 is 1 in 6. Now, because of that nice same value everywhere, this is the idea of a uniform distribution. We'll talk more about uniform distributions in a minute. I'm just using it to get my average. With this, compute the expected value. Let's do that. Each value gets multiplied by its corresponding probability. Interestingly enough, the result is not one of my numbers. When I multiply all these out,
I get a value that's between two of my numbers.
So this isn't an actual result I could roll. You can't roll a die and get 3.5. So this kind of represents the middle. And think about the numbers from 1 to 6. The middle is between 3 and 4, isn't it? Like our median.
We'd get a cumulative chance of maybe of getting a number from 4 and less and a 4, maybe 3 and less, like bringing a number 3, 2, or 1.
But the chance of getting a number 3, 2, or 1, if this is truly uniform, is 1/2, right?
Yes.
And the chance of getting a 4, 5, or 6 is 1/2. And so that middle idea represents this perfectly. As a matter of fact, the mean and the median are exactly in the same place here. That's 3.5. Let's use the PDF we were using earlier. This one. What's the average there? I'll copy this down. Do a calculation for me.
How'd you get 21 in the first one?
How'd I get? Oh, 1 and 2 and 3 and 4 and 5 and 6.
Just added them all.
Well, since they're all on top of a 6, I just multiplied through and then added the fraction. They all have the common denominator, so.
It'd be 2.25.
Aha. 0 times 0.05 plus 1 times 0.3 plus 2 times 0.025, 0.25 plus 3 times 0.20 plus 4 times 0.15 plus 5 times 0.05. So that's 0 plus 0.3 plus 0.5 plus 0.6 plus 0.6 plus 0.25. Now, I believe that the problem I stole this distribution from is number of emergency room visits at a hospital on a weekend night. So on Friday night or Saturday night, how many emergency cases show up at the ER? There's a 5% chance of none of them, 5% chance of 5 of them. What should I expect? I should expect more likely 2 than 3, but either 2 or 3 on any given night. Which means if I stock my emergency room with supplies for 3 cases and staff for 3 cases, then I should be okay most of the time. There'll be rare occasions when I'll be in trouble. I'll have to go back and raid the stock room and do all those other things. Remember our law of large numbers? What's it say?
If you have like larger numbers, it is more likely to happen something.
What number needs to get large and what's more likely to happen? The law of large numbers was about our theoretical probability versus our empirical probability. So there's something different in the way I'm using that here. Back when we defined what the different types of probability were, so that would be what? I think a week ago Wednesday.
N equals 0, 0. So I
Oh, yeah. It looks like this, right?
Yeah.
Then going to infinity. That's our infinity symbol. If our n is going to infinity, if the number of times we do something goes to infinity, our experimental probability should match our theoretical probability. What that also means is that as our number of things gets bigger and bigger and bigger, our average should get closer and closer to our expected value. As we have more and more weekends go by in this emergency room, the average number of weekend cases will be 2.25. That's what this means as an average, as an expectation. If I do this exact same idea as an insurance agent, I would expect it's spring break starting at 5 o'clock today. I would expect that there will be an increased number of automobile accidents in college-age students next week. I hope I'm wrong and none of you have any issues. But if I were looking at large numbers of college students away on break, I would expect the number of accidents to go up. You pay for insurance. What should I expect to be my payout? If I know the chance this accident is going to cost me $100, $200, $300, $400, $500, up to however many thousands of dollars, if I have a distribution function for my insurance payouts, I know what to expect to pay out next week. I know how much I need to charge all of you to make sure I have the money in the insurance pile to pay for all of those accidents. Raffle tickets. I need to cover the cost of printing the tickets, whatever the prize is, and then I need to make a little bit for the people who are running the raffle, right? The lottery. We did this with the Powerball, right? Your chance is 1 in because how much does it cost to run? What's my expected payout? How much do I need to have right now? Cover that. Pricing of policies, pricing of product, pricing of anything you want to try and sell. How many people will buy it at this price point? Where should I sell it? This is the primary job of an actuary, is using these sorts of expectations to determine pricing. All right, so now I have an average. That's a measure of center. Our descriptive statistics next ask for measure of spread. I need variance, standard deviation. All right, wait a second. I told you we weren't going to do these calculations very often by hand. I stand by that, but I should understand how this calculation works. What I need to do is I need to take the average minus, the value minus the average, and then square it. Just a second. But in the same way that I accounted for the value, I'll need to account for the value here. So I'm going to add up the value itself times, the probability, the value itself minus the average. I'm going to square that because that was what our deviation squared. Then I'm going to multiply by the chance of that one occurring. That's my variance. Mother. All right, wait a minute. I have this distribution right here. I have its average.
0, 1, 2, 3, 4, 5. Here are my values. Here are my probabilities. 0.05, 0.30, 0.25, 0.20, 0.15, 0.05. From the calculation we have right above, the average is 2.25. So I take 2.25 and subtract it from 0. And then I square that. 1 minus 2.25. Square that. 2 minus 2.25. 3, 4, 5. I did all these on my calculator already. I wrote them down. Notice that the things that are close to the average have very small variance. I'm so glad they're backing up a truck right outside our classroom. And the further away we get, the bigger those numbers get. Now, I don't want to add these up. I want to multiply by the probability. So take this value and multiply it by each of the chances. So what's 0.05? What's 0.05 times this thing? Now, again, I did this, I wrote this down. 0.253125. 0.3 times this thing. 0.46875. 0.25 times this thing. 0.15625. 0.2 times this thing. 0.112500. 0.15 times this thing. 0.459375. 0.05 times this thing. 0.378125. I need to add up that column. When I add up that column, I get 1.6875. Phew! That's a lot of work. But that's the variance. Here's my problem with this calculation. It's squared, right? This is in hospital visits squared. That's a useless unit. If I take the square root of this, I get a standard deviation. And in this case, the square root of 1.6875 is 1.29903 . We're going to call that sigma, just like we did in our populations. That's a standard deviation here. I can do this directly in my graphing calculator. I can do this in Excel when I use a weighted distribution. Because setting up this calculation in Excel is actually really easy. Setting it up on here means I actually need to put in the two lists. I need to put in the values, then I need to put in the probabilities. And then, when I go to do my descriptive statistics, I need to tell it the frequency list. The frequency list is my probabilities. Second, list 2. There's my average, there's my standard deviation. Yes, sir.
So, if we have a question like this.
If I'm asking you to do variances by hand, you should hit me in the head with a brick. That's the, yeah. Are you kidding me? Oh, no. If there's a question like this on the exam, I need to be burned at stake. Interpreting it, that's a whole separate ballgame. However, the distributions we use most frequently have easy to calculate standard deviations. So when we come back from break, we'll talk about specific distributions, and those will have formulas for the standard deviations and variances. I will see you all then. Enjoy your break.